Okay, now it took a lot longer to get through this than I had planned, so I kind of had to do a short synopsis of the situation where you have the bullet hitting the block. There's several questions involved with the bullet shooting into the block. Okay, so what we have is a 50-gram bullet moving horizontally at 200 meters per second. It embeds in a 2-kilogram block at rest. Then the question becomes, well, okay, what's the velocity immediately after the collision? Well, what velocity? Well, the velocity of the only thing that's moving, which is the block with the 50-gram bullet embedded in it. Okay, so the total momentum before collision has to equal the total momentum after collision, because the impulses are equal and opposite. They add up to zero. There's no net momentum change. Now, we've been analyzing things by finding the impulse of this object and the impulse of that object and the changes in velocity. But we can also do exactly the same thing and get exactly the same results by saying total momentum before equals total momentum after, as you'll know if you've been reading your book. Okay, total momentum before equals total momentum after. In the total momentum before, well, the 2-kilogram block is at rest, so it's just the momentum mv, 0.05 kilograms times 200 meters per second of the bullet. Afterwards, you got just one thing moving, which is a 2.05 kilogram system, object consisting of a block with the bullet embedded. And then that's times your velocity after. And now we can easily solve for the velocity after. It's going to be, well, this divided by 2.05 kilograms. I didn't even write down the kilograms because we see that the kilograms is going to divide the kilograms and go away. So we have the 0.05 over 2.05 multiplied by 200 meters per second, which is pretty close to 5 meters per second. Okay. Now, several things are purported to happen to this block. We've got the situation on the incline, and that is the first one. But let's take actually what's probably the simplest situation, where the mass is on a pole 1.4 meters above the ground, and presumably, implicitly, at least the ground is level. Now we've actually got two situations illustrated kind of together here, so let's separate them. For this situation, well, the bullet hits the block at a horizontal, so the block comes off with a horizontal momentum. Momentum is a vector quantity, and if the only momentum before is in the horizontal direction, the only momentum after is in the horizontal direction. Now that's going to begin, so the velocity of the block at the instant after collision is going to be in the horizontal direction. It's going to be moving at about 5 meters per second. I think it's like 4.95, okay. But getting a little fuzzy right now, staying fuzzy actually, but okay, so moving at 5 meters per second, when we come off of the post, it's going to fall 1.4 meters during the same time that it moves in the horizontal direction. And its horizontal range is going to be what? Well, it takes roughly half a second to fall 1.4 meters. Okay, so falling 1.4 meters in half a second, it's going to get to travel at 5 meters per second in this direction for half a second. So it's going to travel about 2.5 meters. Now you can get the more accurate version of how long it takes to fall and get a little more accurate result than that, but it's going to be pretty close to 2.5 meters, within a couple of tenths of a meter, I'd say. If the bullet happened to hit at an angle, then this projectile would follow a somewhat different parabola. You'd have an x component of its velocity, or component of its velocity in the horizontal direction, and a component in the vertical direction, and you would have to solve the two resulting equations that you're used to solving for projectiles. You'd be able to do that if you've understood projectiles. Okay. Now, another situation, you have a slope at 1/10 of a radian above horizontal. And the bullet hits this thing and gives it a velocity up the incline. Now, it turns out that it doesn't really give it a 5 meter per second velocity along the incline, okay? But at this small angle, which is about, rounding off to the nearest degree, 6 degrees, it's going to be pretty close to this. Okay, the reason it doesn't give it the whole 5 meters per second is only the component of the momentum parallel to the incline is going to influence the velocity. So it's going to be a little less, okay? Probably guessing about 4.7 meters per second, I would say, and you can work it out if you wish. Okay, then we want to know how far this thing goes up the incline. Well, I say this is good, but not really, because that 5 meters per second isn't quite accurate. It's actually going to be 5 meters per second times a cosine of 0.1 radian. Okay? And let's say I did that, and 1% of that would be 0.05. Yeah, I'll kind of stick with my estimate. Okay, well, and excuse the digression, okay? You can use this to solve the problem if you wish, but be aware that it's really this. And then be aware also that the sine of 0.1, meaning the sine of 0.1 radian, because radian is the default unit of angle, the sine of 0.1 is approximately 0.1 because 0.1 is a small number. Now, the easy geometric demonstration of why the sine of a small number is equal to that small number. Okay? But that is the case. It's something you should have learned in trigonometry and pre-calculus or whatever. So, you want to think about that. And it's also demonstrated very typically in the first semester of a calculus course. Okay, well, then the cosine of 0.1 is going to be the square root of 1 minus the sine squared of 0.1. 0.1 squared is 0.01. Subtract from 1, you get 0.99. 0.99 is close to 1, and the square root of a number close to 1 is the number that's twice as close to 1. And that would be 0.995. Now you can punch these numbers into your calculator and see just how accurate this is. It's quite accurate for an angle at, 1/10 of a radian. And then you could figure out what the cosine of 0.1 radian is. And if you multiply 5 meters per second by 0.995, you get 4.75, I think. Of course, the 5 here isn't really 5, it's more like 4.95. That's why I say about 4.7. I think that's what I said earlier, but that's what I should have said if I didn't. Another situation, well, it's the same situation. How far do we go up the incline? Well, I'm going to say we go up the incline until our increase in potential energy is equal to the decrease in kinetic energy. As the kinetic energy decreases all the way to its lowest possible value, which is 0. Okay, so first of all, we understand from the work energy theorem that if there's no dissipative force, no other forces but the conservative force, that the change in kinetic energy plus change in potential energy is 0. So that the change in kinetic energy is minus mg delta y. And that's because negative mg delta y is the work done by gravity, and that's equal to the negative of the potential energy change. I also went on a little tangent about what we mean by potential energy. It's not mgh. It's only mgh in the gravitational field of the Earth close to the surface of the Earth. Doesn't apply if you've got magnetic forces, electrostatic forces, springs, or any of a myriad of other potentially conservative forces. Okay? The change in potential energy is equal and opposite to the work done by a conservative force, which is why the change in potential energy is equal to mg delta y, where y is your vertical coordinate measured in the upward direction. When the potential energy, when the only conservative force is gravity, this works. Only then. Please do not use mg delta y or mgh in any other circumstance. Yeah, we've got time. Okay. So, you know, if this thing moves a distance delta s, how much higher does it move? You've got the angle. You know the sine of the angle. You can figure that out, or you can do that with vectors in any of a number of ways. Here we have the block suspended from the ceiling by a string. Somebody asked, okay, well, what happens if the string breaks? I said, okay, use everything you're going to learn next semester in your strength and materials course and properties of materials. Use all the appropriate properties of materials to model the string as it breaks and work the problem out that way if you wish. But, of course, you don't want to do that just yet. But you know, that was a fun question to talk about, and give you a little prelude, at least for the engineering students, of what they're going to be in for soon. And you know, I just realized I've been pointing to things over here that you can't see. Well, I'm going to stop this video and just kind of catch you up on what's there.